Okay. This is the session 10A, Telecommunications Engineering, and I am Inigo Cuinas. I'm professor at the University of Vigo in Spain. We have a session made by six papers, six works, and each of them will have 15 minutes for as full time for the presentation, 12 for doing the presentation, and 3 minutes for questions and answers. Some questions can be from the other presenters, and others for the public in general, and will be made using the chat in the local Zoom session we are holding in order to do the presentations. So without more introduction, we are going to begin with the first paper. The paper is called Estimation of Bare Bit Error Rate Using Digital Smoothing Filters, and the presenter will be Professor Zeglinski from the West Pomeranian University of Technology in Poland. So, Professor Zeglinski, floor is yours.
I'm ready. Okay.
Okay, you can share your screen.
Okay, it's working. You see. Okay, it's okay, presentation?
Yes, I think so.
Okay, super. This presentation is about method and some measurement results which are doing in West Pomeranian labs in group Jakub Peksinski, Dr. Jakub Peksinski, Dr. Mikolajczak, and Professor Kornatowski. The authors of the works are scientists from various disciplines and departments. Jakub Peksinski and Grzegorz Mikolajczak are persons which are calculated this results. Eugeniusz Kornatowski is experienced scientist, professor in the field of digital filtration and practical application. I am a person which are working in laboratory of teleinformatics technology and photonics. This presentation will be in the second part of this publication about measurement results and simple compared to calculation results. This laboratory has 6 parts of labs. The lab which are conducted with numerical results and which are compared with practical setups. It was made in a laboratory of reference optical teleinformatic networks. This lab has transport part and access part of optical fiber networks with the wavelength division multiplexing, and I show on the next slide this lab. So the second part is laboratory of microstructure optical fibers. This lab has a connection between labs of reference networks. In this lab, we have a lot of measurement devices like optical scopes for bit error rate analysis method. This is spatial devices which are working to 640 gigabit bit rate. This is short view for our labs. This is a lab with reference network and access network. We have two point for transport network with transponders. The transponders are tuned, and and bit rate is 10 gigabits per second in C-band, telecom C-band. The telecom C-band is working from 1530 nanometers to 1565 nanometers, and each transponder is tuned in this band. Actually, we have 88 wavelengths in C-band. It's approximately for 10 gigabits, it's get 1 terabits, exactly 880 gigabits per second. It's possible to use this system for 40 gigabits per second. And in this part, we have 20 parts of single mode fibers with 17 and 18 kilometers, and we can use 70 parts of microstructure fibers, which are agreement with ITU-T G657 ITU-T standard. For measurement result, we make spatial setups to get for various bit rate and for various distance result in eye diagram, which are observed on optical scope. Okay, this setups are preparing by students in our scientific group. Okay, and the problem of distortion, which are discussed in this paper by a spatial numerical method, is in optical fiber is linear. Basic problems is linear and non-linear polarization. In general case, we have this two part of polarization because we are use a relay system with transponder. We can get power approximately in one wavelength 10 milliwatts. It's possible to get small nonlinear effect in one wavelength, but for wavelength division multiplexing we can observe small nonlinear effect. But to get this result, we use spatial system with amplification. We can get general linear effects. Linear effects is described by the first order susceptibility. It's get some spatial parameter in real line, like attenuation of optical fiber, chromatic dispersion of optical fiber. The nonlinear part of polarization gets some information about second order nonlinearity in optical fiber and third order nonlinearity in optical fiber. In glass fiber, we have only this part of nonlinearity, which are called, for example, in spatial cases, optical Kerr effect. In general case, we have some problems of nonlinear effects in optical fibers, which are called parametric gain. It's nonlinear effect with one wavelength in optical fiber, and self-phase modulation is typical nonlinear effect, which are connected with optical amplifiers. In this system, we have to use optical amplifiers on the first step to get a fixed power to input in optical fiber, and the next nonlinear optical effects is depend on wavelength division multiplexing. For example, distance between wavelength. But this effect is observed in result in this calculation, but it's small effect, approximately less than 5%. Okay. If you want to analyze transmission in optical fiber, typical method is nonlinear Schrödinger equation analysis, where we use linear operator and nonlinear operator. Linear operator has information about attenuation, about chromatic dispersion, typical factor of chromatic dispersion, and second order.
Sorry, we're in the last 3 minutes.
Okay. So, okay. In this method, we use time domain split method and frequencies domain split method. It's possible we have 4 steps to analyze this effect. It's analyze linear effect, only loss fiber, chromatic dispersion, and chromatic dispersion we can observe it's typical problem in this result in optical eye diagram. Optical eye diagram is a typical method to get quality of transmission signal. Is described in fundamental telecom books, fundamental telecom papers. Important is use this eye diagram, which are described by Q-factor parameter, to get a spatial algorithm, and we get spatial results, measurement results to prepare this algorithm. We use spatial wavelength to prepare this algorithm, make a lot of setup to measure each point which are presented in paper. And next last point, it was prepare simple method to observe distortion in optical fiber line, and it was spatial method, Q-parameter estimation by use smoothing filter method. It's a very useful method because we can good connection between signal and distortion, and we define spatial Q-factor for this method and get measurement result, calculation result, and method result with good agreement. We have good agreement with model to measurement result. And one important conclusion, this method has good agreement to 10 gigabits per second, but probably is very useful for high rate transmission system like 40 gigabits per second, and actually we can use this method to 40 gigabits system. This is described in this paper, and the method will be testing actually in spatial measurement system with 100 gigabits transmission and 400 gigabits transmission. Thank you very much. The results is the all result is described in paper.
Okay, thank you very much, Professor from the public or from the other presenters? Well, I could do one question about the time of your proposal to be part of a real system. So, what do you think about the applicability of your proposal in real world systems in the next months or in the next years?
Important problem for this system is coding method. Actually, we use non-return to zero coding method. In next system, we can use return to zero system, coherent system. It will be important to find very good Q-factor estimation for this transmitter system. Q-factor is parameter which are not described in ITU-T standard. It's typical numerical factor, and we can get, for example, bit error rate for standard. In standard, we have definition. We have definition only bit error rate and correction with bit error rate. I think it will be very important for 400, 600, 800 gigabit system, and for NG-PON2, for example, and for 6G fiber to the radio system.
Okay, thank you very much, Dr. Zeglinski. We don't have claps to thank you.
Okay.
And now we move to the second word.
Moment, I have a was.
It's titled. I think that Professor Inna Kurbatska from Riga Technical University in Latvia could get the control and share her screen. The presentation, the paper is called Evaluation of the Performance Affecting Factors in the Converged Optical Network, and the presenter is going to be Inna Kurbatska from Latvia, from Riga Technical University. So, Professor Kurbatska, the floor is yours.
Thank you. Good morning. My name is Inna Kurbatska, and I would like to present you the results of our paper, Evaluation of the Performance Affecting Factors in the Converged Passive Optical Network. Okay, I will start with motivation. Why do we need such a research? When I will describe the aim, the idea of this research, when I will show you our simulation setup and describe the results and finish with our conclusions. So actually, today we know that significant interest in 5G enabling technologies is very significant interest in 5G enabling technologies. At the same time, now fiber optical access networks are considered as the most appropriate candidate to ensuring the front haul for these technologies, utilizing radio over fiber technology. From this, we see new challenge for this access network. Actually, we need to ensure coexistence of already working technologies of this network with this new radio over fiber technology. So actually, there are a lot of studies in ROV implementation in passive optical networks. However, the main part of these studies are proposing of new architectures or separate solutions. Of course, this is important. However, if we speak about standardization, there is no certain solution that are chosen by the standardization agencies. That means that research should be performed for a widely applicable solution. Actually, if we provide some general results, we will be able to use them for different architectures that will be chosen in future. Actually, this work is a part of project where we work on mathematical modeling. For this purpose, we think what can be useful for this topic from the side of modeling. And actually, modeling gives us a good opportunity to provide general result in estimation of different impact factors, because in modeling we have wide opportunities to switch off or on some effect. And actually this is the goal of our research. We want to provide the independent evaluation of different performance affecting factors for the system, and in such a way we define the most important transmission impairment to deal with in the case of converged passive optical networks. So here you can see our simulation setup. It was developed in VPI Design Suite software, which is widely known for fiber optical network simulation. And this is a typical architecture of passive optical network. Actually, we have central office where we have optical line terminal with two parts. This already existing part, fiber to the home, internet for users, and this is a new part, radio over fiber part, when we combine these two channels and transmit over optical distribution network. And when in subscriber premises or customer premises, we have receivers where we receive the transmitted signals. Further, I will describe a little bit in details each part. So here you see optical distribution network, where we combine these two signals. For this purpose, we use ideal. Actually, we perform simulation, so we use ideal optical multiplexers with the bandwidth of 75 gigahertz, which is typical. For all other elements, for example, fiber, we use as a basis parameters from the specifications of real fibers. Yes, and here we combine two channels. Radio over fiber part has 3.5 gigahertz frequency with QAM OFDM modulation, and in optical domain it is transmitted at 193.1 terahertz frequency, which is C-band. And typical fiber to the home channel is with 10 gigabits per second and corresponds to XG-PON standard. And here we provide a 100 gigahertz channel spacing because we will study the possible impairments of this channel. So we have chosen typical spacing for passive optical networks to study this impairments. Yes, here optical line terminal with radio over fiber part. Here you can see electrical OFDM transmitter where we get electrical signal, where we send this electrical signal to Mach sender modulator, and in such a way we obtain optical signal. Here is continuous waves laser, which provides carrier frequency. Also here, all elements as laser and the modulator were all based on real specification. Yes, and as a result, at the output, we obtain radio over fiber signal with the power of 1.5 dBm. And receiver part, also for off part, I do not include here in detail description of XG-PON signal as it's widely known and studied. All focus was on ROV part. Yes, actually, we have receiver based on pin. Oh, sorry, here I have mistake in picture. Okay. Actually, in ROV part, we have pin photodiode with the limited bandwidth and with parameters also based on real transmitter. I will return and I will show in the topic here with this last picture. I'm very sorry. Yes, we scanned. Yes, and now about our results. We started with investigation of ideal model, actually with only radio over fiber channel, and we tried different parameters. The goal of this case was to evaluate at the beginning impact of electro-optical modulation, as well impact of signal transmission. So here you can see results. So what we concluded from this first step. First of all, we see that the impact of transmission is not significant because you see that the difference between back-to-back 10 and 20 kilometers is not significant. Here, yes, for this case of QM16, we have some difference, but the simple error rate is very, very small, so this is not practically significant difference. So from this, we conclude that presence of simple error ratio, because electrical signal was ideal. So for this case, simple error ratio was 0. So there were not errors. So we conclude that all simple error ratio in this case is due to the process of modulation and demodulation. So we see first significant impact factor. Yes, and also from these results, we defined the signal, what we will use for further research. We took 32 QM and 16 carriers because here we see sufficient reserve to continue our investigation. Yes.
During the last 2 minutes, sorry.
Okay, yes, I will try faster. Okay, when we evaluated dependence on the bandwidth and impact of transmitter and receiver bandwidth, and from it, we concluded that we have significant impact of bandwidth up to 20 gigahertz, and we observed an unexpected tendency that this impact is more significant for smaller data rate. Yes, after that, we evaluated impact of existing network XG-PON, and this was not significant. Yes, after that, we combined these two factors, and also we see that in the case when the XG-PON present, we have more significant impact of the fiber. Yes, next one was impact of noise regarding the received optical signal power. And here we see that, again, XG-PON doesn't affect something significantly, but noise and power are very important. Yes, and here again we tried what will happen if we change dispersion, increase dispersion coefficient for the fiber, and here we see Again, XG PON impact has not changed, but with impact of dispersion also is not very significant. And summing up, we have demonstrated that the main impact factors are process of modulation, the bandwidth, and the signal power in presence of noise, which actually means signal to noise ratio. Transmission over fiber also has some impact, but it's not so significant and is crucial for higher baud rates. And we prove that coexistence with the existing systems is not very important factor, and it has not impact on this new signal. Yes, that is all. Thank you for your attention.
Thank you very much, Professor Kurbatska. Do we have any questions from the public or from the other presenters? Well, I could have a question. Once you demonstrate theoretically that and practically that the use of optical links with a real broadband is valid in 5G systems, what do you think about the possibility of the implementation in the standard of such elements in a full operation? I mean.
Actually, I have not understand. Could you repeat?
I thinking on the possibility of moving from research to real world applications. So the possibility of
experimental research, yes.
Yes.
Actually, of course, also our institute works also experimentally. Just my specialization is on modeling. That is why I focus on this part. So that is why. Okay,
thank you very much. And we can move to the third paper. The third paper is titled Threshold-based wireless-based NOMA systems over log normal channels, ergodic outage probability of joint time allocation and power splitting schemes. And the presenter is going to be Professor Lukas Sevcik from the University of Žilina in Slovakia. So I think that Professor Sevcik, yes, Professor Sevcik is there. So you can share your screen and begin your presentation. So the floor is yours.
Yes, thank you very much. Can you hear me?
Yes, perfectly.
Probably now I share my screen.
Yes, this is perfect now.
Okay, thank you very much. Good morning for everybody. I would like to present our paper today. It is paper on which we cooperate with University of Vietnam. This topic is main idea of my colleagues. I think that it's really interesting, and I would like tell you something about the motivation, introduction. After I would like introduce our model. And some parameters to the model, and after I will conclude the paper. Something about the motivation. Due to the development of the 5th generation communication 5G and also IoT, Internet of Things, the demands for the capacity and throughput of wireless network have increased significantly. This is the reason why we chose working with radio access technique and concretely NOMA technologies, what means non-orthogonal multiple axis technologies. In this paper, we analyze the system performance of joint time allocation and power splitting protocol (JTAPs) for NOMA technology for energy harvesting wireless networks over indoor scenarios, which we model with log normal flooding channels. As a next, the analytical expression of metric, so-called ergodic outage probability, was derived for the performance analysis of such networks. For the analyzing, we used Monte Carlo simulation created in MATLAB. We are able to see how different energy harvesting, power splitting, and also energy harvesting time switching factors influence the ergodic outage probability. After we plot the simulation results and we compared our result with theoretical result, I will show you later in the graph. Yes, some introduction to NOMA technologies. Maybe I need to tell that non-orthogonal multiple axis can support connectivity with low latency, high reliability, high throughput. Besides, we can gain benefit from the deployment of multiple devices by using simultaneous wireless information and power transfer (SWIFT) technology. And systems with NOMA and SWIFT technologies significantly outperform the orthogonal multiple axis when we compare with OMA orthogonal multiple axis systems. Being this, the device users can harvest energy from the source signal. They can power themselves, provide higher throughput and energy efficiency. Usually, the flooding channels are specified by popular outdoor flooding models such as Nakagami-Rayleigh model. As a matter of fact, that only a little attention has been paid on indoor flooding models such as log normal flooding. We decide that in this paper we will use ergodic outage probability of J-step scheme in a NOMA. Now you can see our system model. This figure illustrates model with base station and two users. One user is a user near the station, which is green, UN, and second one is user far from station. It had blue color. And to avoid the obstacle between station and the user far, we have data sent from base station to user near and then forwarded to user far, as you can see in the figure. GRBV operates user near with user far mode and hold it with the energy harvested from the base station. Additionally, we denote the distances between base station and user near, and between user near and user far as DA and DB with complex channel coefficients, as you can see, HA and HB between these nodes. We consider in our model two independently and identically random variables over the block time following log normal model. which are respectively which are also compute as ln. The evaluation of these parameters also for the mean value and standard deviation you can see on the figure. And for the hybrid joint time allocation and power splitting, the transmission time is split into 3 blocks. You can see it in the table. First block is alpha t, and after is 2 blocks, 1 minus alpha t divided 2 with the switching factor. The first compound expression, it means middle column in the table. Within user near receives signal power as PS from base station, respectively for energy harvest and data transmission from base station to user near with power splitting, which is factor beta shown on the figure. And within the second block, we use all the harvested energy for data transmission from user near to user far. Here you can see computing of performance analysis from base station to user near, which include energy harvesting and information transmission. On the figure, you can compare the harvested energy at the user near for the all parts energy harvesting blocks, as I told on previous figure, for alpha t and for the next 2 blocks. It should be noted that from power allocating perspective, we should assign more power to user far because it is located further from base station that user near. In our paper, we analyzed the system performance with a metric, namely Ergodic outage probability. It stands for the probability. It means
we are in the 3 last minutes, please.
Okay, thank you. Capacity drops below the thresholds. Okay, maybe I will be more quickly. Now I would like to tell you something about the results. We study how power splitting and time switching factors of the GTAPS protocol affects the system performance of NOMA technologies. We used log normal flooding channels. There, here is parameters for our model. When W means bandwidth, eta means energy efficiency, M means path loss, D is distance. And now I would like you to present some our results on the figure. I'm sorry. On the figure you can see figure 1 and figure 2, which illustrate the ergodic outage probability of user near and on the left side and user far on the right side. It is with a fixed factor alpha, which means time switching. We set it to 0.3. We investigate relationships in the different threshold cases. As you can see, threshold C is set to 1/2, 1, and 2. We can observe that in both cases the lines is very similar. The curve trends are similar. The lower the thresholds means that the more significant curve in comparison with the others. Besides the lowest threshold value means 1/2, C set to 1/2. This set performs the best with maximum ergodic outage probability of 0.66 in the case of the user near. Specifically in figure 1, the free curves gradually rise in association with the increase of the energy harvesting power splitting factor until they reach their maximum values in power splitting. In the figure 2, the free curves are slightly convex. They decrease at first to reach their minimum, and after quickly rise to their maximum values, as well as the maximum ergodic outage probability of 0.52 in the case of 1/2. And here I can present you ergodic outage probability versus the varied time switching factor. In this case, power splitting factor is fixed, and it means that beta is set to 0.3. We analyze them as well in 3 different cases about the parameter C. In the same manner, the lower C means the higher the system performance, also on both sides, also for the user near and user far. Specifically in figure 3, the ergodic outage probability is in the highest at alpha 0.6 for C2, 0.8 for C1, and 0.9 for 1/2. Additionally, figure 3 and ergodic outage probability level is the lowest at alpha 0.4, 0.5, and 0.6, and after after is a really high peak at alpha 0.6, 0.8, and 0.9. Okay, I will conclude to conclude our paper and our results. We investigate the ergodic outage probability of hybrid protocol, so-called GTAPs, for NOMA technologies for energy harvesting. We use log normal flooding channels. Thanks to Monte Carlo simulation, we can able to assess the impact of different energy harvesting, and we can compare power splitting and time switching factors and their influence to the system performance. We can show you that our results with comparison with the theoretical results are not same, but really close to the same, and it means that this simulation is suitable for next research and maybe for next paper. Okay, it's everything from my side. Thank you very much for your attention.
Thank you very much, Professor Sevcik. In order to try to keep the timetable, we are going to move to the next presentation, which is titled programmability of connectivity control, and is going to be presented by Professor Atanasov from Todor Kablesov University of Transport in Sofia, Bulgaria. So, Professor Atanasov, please take please share your screen to all of us. Hello?
Good morning.
Okay.
Unfortunately, what I see is that I can't share my screen until another one is sharing.
Oh, no,
okay.
Now it's okay.
Now, thank you. In a second. Okay. So, good morning again. Me and Professor Pencheva, we are trying to do some research on programmability of connectivity control. So this my presentation will do the following schedule, and I will try to run ahead of the schedule because I know we are a bit late. So the outline is as follows, and first some introduction about the related works and especially the motivation of the programmability of multi-connectivity control. Next, the connectivity control itself is described as a service with data structures and entity types. What is coming next is the math models about the behavioral settings that are used for formal service verification. And at the end, it's the theoretical evaluation of the service functional performance and some performance tests that are aimed to evaluate of injected latency of our model. Finally, the conclusion, of course. So, about the introduction and the multi-connectivity itself, this is a feature which allows the user device to have simultaneously multiple connections to the network, even using different radio technologies. So what we do in this paper, we investigate the capabilities to open the radio access network interfaces for third-party control on multi-connectivity in fifth-generation networks. So Open Radio Access Network is an initiative for radio access network virtualization empowered by the principles of artificial intelligence and cloud computing. RA and openness enable fast introduction of innovative services and network customization. So the edge computing makes possible the usage of artificial intelligence for traffic steering, quality of experience optimization, and quality of service resource optimization. While Open Radio Access Network focuses on use cases and deployment scenarios, we propose an approach to virtualize the multi-connectivity functionality and to enable third-party cloud applications deployed at the network edge in order to make intelligent decisions about device connections. And, okay. So, the related works regarding especially about the benefits of multi-connectivity and about the advanced architectures, protocols, and schemes for multi-connectivity, and about network cloudification on demand as resource sharing, and finally about the core network cloudification and programmability. So, okay. Our humble contribution is going to be in the exposure of radio access network functionality of connectivity control to mobile edge applications. So the proposed application programming interfaces enable edge applications to configure multiple radio links to a given device in order to improve the, for example, reliability and spectral efficiency. Opening the network edge for this functionality enables applications deployed at the edge to influence the device connectivity based on local policy, actual radio network conditions, device location, or context. Oops, sorry. Yeah. So, ultra-high reliability, enhanced bandwidth, and strong security are required in different use cases envisaged in next-generation networks, such as industrial automation, smart grids, tactile internet, etc. Multi-access edge computing provides a cloud environment for applications at the edge with requirements for low latency, high bandwidth location, and context awareness. So the edge functionality may be extended with exposure of connectivity control. Okay. Now the next one. The open access to connectivity control may be provided by a new service called by us Multi-Radio Dual Connectivity Control Service, which enables applications to access information about device-supported technologies, to configure device measurements, to access measurement information, and to add and remove a serving node. Okay. Next one. So in a dense environment, a dedicated edge application may configure connectivity-specific triggers for measurement reporting. So, for example, a white list of cells or black list of cells, which are not applicable in event evaluation or measuring reports. They are not considered there. So the application with an active subscription may receive notifications about device measurements when the application-specific thresholds are reached. So the figure shows the flow for application query about device capabilities, subscription, and notifications about connectivity-related measurements. Okay. The logical representation of entities related to connectivity management are described as resources. So the resources are manipulated by the well-known hypertext transport protocol methods. When the application decides to provide additional resources from a target node to the user equipment, it sends a post request for adding the target node to the node which is at the moment the master node, and the secondary node, which is the addition or modification procedure as executed in the network. Okay, good. So the edge application uses a put request to modify the node added by itself, or delete request to release the node, and the modification procedure or release procedures are executed in the network, respectively. Okay, let's go to the data now. In a second. My PowerPoint is gone. So the data model is a part of service interface definition, and it describes data structures and entity types. The data model is designed to encourage interoperability and application collaboration, increasing agility in development. So enough about the data, and the service resources are organized in a tree structure following the service route and uniquely identified. The service route may be published in the registry of the services. The resources represent queries about device capabilities, measurements, and radio access nodes added by the application. Okay. So The application development that uses the service interfaces requires modeling of the device connectivity state. So this model must be harmonized with the device connectivity model maintained by the network. From the network point of view, the device may be connected to a master node and to a secondary node. So the network maintains device connectivity models for the master and the secondary nodes respectively. The models representing the node state from application, master node, and secondary node point of view are formally described.
We're in the last 3 minutes, so please.
Okay. And using the concept of weak-based simulation, it is proved that the models expose equivalent behavior. Good. Going further, so the functional performance metrics of mobile edge services impact on the perception, and the latency injected by the application-initiated request for adding or releasing of a node may be evaluated as the time required to notify the application about the measurement thresholds reached or to enforce application-initiated action. So the prototype of the service as a REST-based one is done by using Apache Cassandra and Vertex, and the numerical results show that the most of the operations would add to the latency budget around 3 milliseconds, yet some spikes go over, well over, beyond 1 second. And concluding, I would say to add up, because my time is over, I think, the opening the interfaces of radio access network for third parties enables fast creation and deployment of applications. We are trying to propose a new mobile edge service which exposes the network functions for device connectivity control, and it is evaluated and emulated. Thank you for your patience and kind attention.
Thank you very much, Professor Atanasov. Does you have any question? I don't think so in the chat. I only have a question. It's related to how close or how long do you think is the possibility of introduce this new mobile edge computing service into a broad standard like 5G?
Well, they are already standardized by European Telecommunication and Standardization Institute, ETSI, and having some specifications. It depends on the mobile operators. If they want to make some money about for example, the augmented reality or any kind of such applications, they should put some cloud abilities at the edge of the network. Doing so, you got the services there and you make business. So we are trying to profess that it's profitable to distribute the services at the edge because of the closeness to the users, to the end users.
Okay, thank you very much, Professor Atanasov.
Thank you.
Now we move to the next contribution that is called Performance Evaluation of OBS WDM core node using queuing theory, and it's going to be presented by Professor Hani Ali Harb from Al-Baha University from Saudi Arabia. So, Professor Harb, do you have the floor for you?
Thank you, Professor, for inviting me to present my paper. I am assistant professor Hani Harb from Al-Baha University, Computer Science and Information Technology.
Sorry. Please, Professor Atanasov, mute your microphone, please. Thank you very much. Sorry, Professor Harb.
Never mind. Our paper today is titled The Performance Evaluation of Optical Burst Switching WDM core node using Quyet-Nguyen theory. Here's our, I will try to be fast and inshallah finish it early inshallah. This is the outline. First, the abstract instruction, system model, and theoretical equations, and then I will give the numerical results and conclusion and our intended future work. This paper studied the performance of optical burst switching WDM core node using a recently proposed analytical model that based on the Quyet-Nguyen theory rather than the previous models, which is depending on the designing factors of or the physical factors of the optical burst switching core node. The main parameters they calculated are the time delay and blocking probability. As a result, we find that our new model is simple, fast, accurate, and give similar results, almost similar results compared to the other models. As we know, WDM systems or networks have attracted much interest in the past 2 decades and become an important tool in the data communication. That is because the huge bandwidth that it can provide, and one of the challenges in this network is the switching techniques. One of them is the optical burst switching, and it is lie in an intermediate region between the optical circuit switching and optical packet switching. Almost the current technique is the optical circuit switching, which is based on switching which is the basics used switching technology in the optical network, but it suffers from a lot of drawbacks. It is not easy to adopt rapidly dynamic variety traffic, and it's also suffer from a huge delay. Also, the optical packet switching have its own limitation due to the limited buffering capability and the lack of high-speed logical processing. So, optical burst switching seems to be the most applicable technology for implementing WDM system. It also have three schemes. First one is still and go. The second is just in time, and just enough time. We have published maybe 3 papers on the optical burst switching, and we suffer from using a very complicated models. So we use a recently proposed model to just check our previous results and to evaluate the new approach. We select in this paper the second scheme of burst switching, which is just in time, because the nodes receives the resources, reserves the resources as soon as a control packet is processed. The source transmits the payload in the optical burst switching, the control packets is separated from the payload and are sent separately. The source transmit the payload after an offset which is greater than the processing time of the control packets at an intermediate node. So the payload contains offset time equal to the total amount of the time required by the control packets to reach the destination. So the buffering is not needed. As I mentioned, there are a lot of mathematical models that have been proposed to reduce the blocking probability. However, the majority of them are so complicated to analyze the performance. This paper, we used the model to evaluate the performance of the optical burst switching core node based on the measuring the burst delay time and the blocking probability. Then compare the results with other models. This is the optical burst switching core node architecture, which consists of the incoming DMUX at the left, and then the optical cross connect, the switch control unit, and the outgoing DMUX. As we've seen from the figure 1, that the control, which is red, is separated from in vertical red, which is separated from the payload, and they are sent separately. Based on the basic structure, the basic architecture of the core node, we built the theoretical model in figure 2. And considering the blocking probability of each component in the architecture. Then we calculate, or we build the mathematical model. We calculate we suppose suppose that based on the mean arrival time of the incoming DMUX, we build our calculation. We calculate the mean arrival time in each component, and also we calculate the mean service time, the mean service rate for each component. Then the number of traffic, which is the parameter included in the proposed procedure to evaluate the blocking probability for each component also. And then in equation 9, we calculate the average delay time and the blocking probability in each component, as we see in equation 10 and 11. Then the average blocking probability is calculated according to the equation 12. Here's our numerical result, which shows the average number of traffic
We're in the last 3 minutes, please.
Okay. In HQ, which shows the average number of traffic in HQ with the traffic. As we see here, the Q4 is the biggest. Present the biggest blocking probability. According to that, it is an optoelectronic device, so it is logically. Yeah. We also build we also make the relation between the average time delay and the traffic, also the overall blocking probability in the system, and then we compare the results with the results we have before using another model. It is give the a near results with our model that we used before. Here is the conclusion. As we see, the performance of the optical burst switching WDM4 node using Quyet-Nguyen theory is evaluated based on the calculation of the delay time and the blocking probability in each element of the node structure, then calculating the overall average blocking probability of the node. The analytical model we use it is very simple, fast, and accurate, and than other models, and showing similar results. Finally, this model is suitable for dealing with the system performance, overall system performance. However, other models describes the dependence of the performance of the traffic parameters, such as the number of wavelengths, also the length of the burst, as well as conversion capability. Thank you, and
Thank you very much, Professor Harp. Do we have any question? You can put something in the chat if you want. Well, just a short question. Do you think your system, or what is the improvement of your proposal regarding the traditional or the previous models used to study the performance of this kind of core nodes?
We believe that finding a very robust model to evaluate the performance in an accurate way will help to design, would help us to design a very robust optical system. Yeah. We have a previous publication in this area, and we used another models. I think this model will help to any designer to fast evaluate the performance of its system, of his system, without getting deeply in the each designing parameter of his system. Yeah. It is a very fast and accurate model to evaluate the overall system performance as an indicator for the optical performance of the system, of the optical switch. Yeah.
Okay, thank you very much, Professor Harp. We move to the last presentation of this session. So the title of this presentation, of this contribution, is Heterogeneous Wireless Sensor Network, the Development and Deployment Based on Sensor Nodes Density. And the presenter will be Professor Zeglinski from Riga Technical University in Latvia. So,
Hello. Hello.
Okay. Professor Zeglinski, you get the floor for presenting.
Can I see my presentation?
Yes,
Yeah,
perfectly.
Okay. Thank you. My name is Zeglinski. I'll walk.
Could you switch on the camera, please?
Just a moment. You can see me. Oh. I don't know what is the problem. Wait. Sorry.
Sorry, it doesn't matter. You can begin.
Okay.
Don't worry.
Okay. But our work name is Heterogeneous Wireless Sensor Network Development and Deployment based on sensor node density. Why I need wireless sensor networks? For example, this wireless sensor networks needs to read parameters about temperature, humidity, pressure in the building engineering systems, and the sensor number is much more than, for example, 100 sensors, and it's necessary to transmit data over one channel, increase the probability of the network, and exists a problem of low connectivity resulted by the fragmentation of the network into unrelated groups of nodes. And our works studies a new stochastic characteristic of the quality of a heterogeneous wireless sensor network, this network functioning, and which expands the concept of connectivity. And our work shows the calculation of a heterogeneous and combined wireless networks such as Zigbee, Wi-Fi, and 5G networks. To access the connectivity of wireless sensor network and its viability, it is advisable to use indicators that consider the probabilistic topology of such networks. The geometric sensory nodes and arbitrary territory we can see in this figure. For example, a sensor node in the center of a cycle with radius beta covers the cycle completely and detects a change in physical states inside it. An area with a radius small shows the operation range of a sensor node connection. And sensor nodes with a distance between them being less than small r can directly interact with each other. This picture describes signal changes passing the obstacle. For example, walls, furniture, and other obstacles inside a building interfere with radio waves, and it also causes diffraction of obstacles, radio wave attenuation at distribution on distance, and passing of objects. And in this distribution of a signal, this trajectory changes instead of a straight line, and it becomes a broken line. And in this road passes through several nodes that perform functions of a transfer, and then the probability of a road between two nodes will depend on the length of the road and the probability of a connectivity of these nodes. The connectivity of various sensor networks is measure of a relationship between any sensor node and the data center. The probability of connectivity depends on the number of transfer sensors that must cope with the data stream. And for the probability of connectivity, the following equation is valid in the slide. The event which coincides in delivering data to the head sensor node will occur only if transfer nodes for each transfer are found. In this slide, we can see a heterogeneous network. It consists of fragments of different topologies and different types of tools like workstations, sensors, servers. In different connections of the network, different environments and data transfer protocols was used, such as Zigbee, Wi-Fi, or 5G. To access the quality of function of heterogeneous network, it is proposed to use a 3-node coast network of Quyet systems. This is what we see, 3-node coast network. The data transmission route follows the path from the 0 node to the first access point and then to the second node. And to forward the packets and acknowledgement is sent from the access point. In this model, the 0 node simulates Zigbee sensors. Let's send request to the base station, to the first node, and then to the 5G base station, to the second node. The first node simulates a Wi-Fi access point. The second node simulates a transfer data between the Wi-Fi access point and the base station. For example, this is 5G technology. In this slide, you can see approximation function of a good put is shown in a figure. Goodman is mean the number of useful data bits transferred by the network. For example, the data processing intensity is equal to mu0. T0 is the time interval of the node density P, and epsilon 0 is the performance of the Zigbee network. And usable data rate in this network depends on the distance to the base station. And to estimate the model parameters, we can assume that over time for processing data at the nodes obeys experimental distributions. Experimental data on the influence of the object's distance from the Wi-Fi base station on the data transmission rate we can see in this figure. Mu1 will not be a constant value, but a variable in accordance with figure and to evaluate the system. It is necessary to know how the number of active sensors in this access point zone we have. At the second node, the transmission is carried out in packets of certain length and in the order of packets received from clients. And it should be noted that the packet transmission time can be estimated only as ratio of the packet length to the nominal rate. Since there is a loss of time when establishing and disconnecting a communication session and when transmitting packets. And it's experimented to required experimentally estimate the real packets, transmission time, and the density of the packets processed in the third node. The data transfer time in this section should also be estimated experimentally, since the normal speed is always less than the actual one. And data transmission in this section of the network can be carried out using 5G technology. In this regard, both the first and the second technology we are studied experimentally. In this slide, you can see Zigbee protocol, which is protocol sensors, which is used for XBee sensors. Up to 30 sensors can be connected to one XBee model. It follows if at one point in the time all the sensors connected to the XBee model is being to transfer data to a server. And then I can determine the performance of the XBee model. The performance of the base station is related to both the parameters of the very sensitive networks and the distance from the base station. results mentioned. The model involves the number of n. N determines the number of data transmission sources, which complete to share to the resource of the nodes. This is this number of sensors in the access point coverage area. The complete task is output from the EO subsystem, and instead a new one is loaded from it. While the output stream is equal to the input and from the condition of balance of
in the last 2 minutes, sorry.
Oh, okay. We can use equation inside. As a result, we can see that good put is associated with both the number of active sensors and the characteristics of the Zigbee and the Wi-Fi network. And figure shows for each sensor n at a specific time, packets per second. And based on raw data obtained as a result of the experience, a model was developed which was used to determine the real data transmission rate in the sensor network depending on the number of n requests that is staying in the coverage area of a base station. Conclusion that our work proposed a new stochastic checklist of the quality of the function of our sensor network, spin connectivity. Based on the data obtained, we can conclude that the good put of base station related to the traffic parameters and the checklist of the data transmission system. A model was developed to determine the real data transfer depending on the number of active sensors, the coverage area of the base station of various networks. The resulting three-node model for calculating the good put of a heterogeneous network concerns a model of connectivity of sensor networks, signal and financial from both, signal from the distance to the base station. And thank you for your attention. Any questions?
Thank you very much, Professor Brzezinski. Do we have any question? Not in the chat. Just a question. Did you consider the different models for outdoor or indoor propagation in between the nodes for the attenuation or the effect in between different node sensors or sensor nodes, or you only apply one of them just relating to the distance?
We apply only one sensor therefore for experimental model, and we have experts in indoors, only indoors.
Indoors, okay. Thank you very much, Professor Brzezinski. And this is the end of the session. We had 6 different topics related to telecommunications engineering, related to last generation communication systems, with both wireless and optical proposals. I would like to thank you very much for your interesting contributions, and I hope your research will be successful in the future. And also, we hope, I think, extending to the organizers, we hope to see you in Palanga next year. So thank you very much. This is the end of the 10A session, and we close for till 11 Lithuanian hour in the next session. Bye.
Thank you, Inigo.
Thank you.
Thank you very much. Bye.
Bye.
Bye-bye.
Bye.